Okay, when you guys were dealing with all of the solubility rules, there were lots of things that you read through that were always like, these things are always soluble, these things are not soluble, and these things are slightly soluble. And there was always that question of like, does slightly soluble count as being soluble? And I'm like, no, it doesn't count as being soluble. But really, they actually are a tiny bit soluble. And even though even the ones on the solubility chart that say they're not soluble, they're kind of a tiny bit soluble. It's like the weak acids. How with strong acids you have 100% dissociation. Those would be like the soluble salts. And weak acids would be kind of like the insoluble salts, where they do actually ionize. A tiny percentage of them actually do break apart into ions. So it's the study of the solubilities of the insoluble ionic compounds. So this SP just stands for the solubility product. So it has to do with the whole solubility thing. Now anytime we write expressions for K, it's products over reactants. And so there's nothing different here. We're dealing with concentrations of everything on the product side of the reaction over the concentration of everything on the reactant side, and then to some whatever power of the coefficient that's in front of it. When we're dealing with KSP, we're dealing with solids that dissolve and ionize, and those ions are aqueous because they're dissolved in solution. So only the aqueous stuff is included in the expression. So what that means most of the time is that this reactant part is left off, because we'll see in the equation that that's usually solid. Now the larger the KSP value, the greater the solubility is. There's a whole chart on page 718 that shows you all of this KSP values. And again, the K value here, it's just it's like a ratio of how many products you get compared to how many reactants you started with. So it's a ratio. So the bigger the KSP value, the more soluble that compound is. There's a whole long list here of everything that's considered insoluble and what their KSP values are. And you can see the numbers go anywhere from like 2.4 times 10 to the negative 5, and then some of them, lead phosphate is 1 times 10 to the negative 54, which is a super tiny small number. It's pretty much not going to ionize. Maybe a very tiny percentage of it will. So this tells you how much it's going to ionize in solution. All right, when you're writing KSP expressions, you need to figure out the dissociation first that takes place. So for magnesium phosphate, if I have magnesium phosphate, and these are all considered equilibrium equations, because when they dissociate, some of those ions will join back together and then some other ones will break apart. So you have an equilibrium situation. And so when this ionizes, I'm going to end up with 3 magnesium ions and 2 phosphate ions. When I write out the KSP expression for that, and then you're always starting with solid stuff. So magnesium phosphate is just a solid salt. When you put that in a water solution, you get some tiny percentage of magnesium ions, tiny percentage of phosphate ions. So when I write the KSP expression of products over reactants, the reactant is the solid magnesium phosphate. So that's not included in the expression at all. The only thing that's included are my 2 aqueous products. And so my KSP expression will be the concentration of magnesium ions, and then raised to the 3rd power, whatever the coefficient is, that's what your exponent becomes, multiplied by the concentration of phosphate, and then that one would be squared. Okay, so similar similar idea on writing the expressions. Are there any questions? All right. Most of the rest of the notes are examples on how to use the KSP values to figure out lots of different things. If they don't give you the KSP value in the problem, then make sure that you look it up in the chart on the page number that I gave you on page 718. But here I have silver sulfide, which is really one of those insoluble compounds, but there's a tiny percentage of it that is going to dissolve, and I want to figure out what is the molar solubility of silver sulfide, and they give us that KSP value 1.6 times 10 to the negative 49. That's a pretty small KSP value, which means that you're going to have a very small concentration of ions in the solution. When it asks you to figure out molar solubility, it's basically an ice table question that you're solving for X for. Just like how with weak acids we solve for X and it was the concentration of hydrogen ions, it's the same process. The only difference is that we're solving for the actual ions of the salt that ionizes. And so if I start with silver sulfide, Ag2S, and the tiny bit of that ionizes would give me 2 silver ions and 1 sulfide ion. Now this is solid, so I don't care about it as far as setting up the ice table. These ions are aqueous, of course. All right, so my starting concentration of those, before it ionizes at all, my starting concentration here is 0. And plus 2x gives me 2x, and then plus x over here is x. Now if I write out the KSP expression, KSP is going to equal to my silver ion concentration squared. Squared comes from the coefficient of 2 in front of silver. And sulfur ion concentration. Okay, then you just take what you have at equilibrium right here and you plug it into the equilibrium expression. And then you can solve for x. Now when you solve for x, because the question is what's the molar solubility? When you solve for x, that is the molar solubility. Because if you figure out the concentration of sulfur at equilibrium, the ratio of sulfur to this silver sulfide over here is 1 to 1. And so whenever you solve for x, that is actually calculating the molar solubility. And so if I just go through here and I plug in my KSP value was 1.6 times 10 to the negative 49. And that equals 2x squared times x. And we've done all of this solving for x many times. X is equal to 3.4 times 10 to the negative 17 molar. Whatever you get when you solve for x, okay, you can use that to figure out concentrations at equilibrium. So that would be my concentration of sulfide ion at equilibrium. If I wanted to figure out the concentration of silver, then I would just double it because silver is 2x. But whenever you solve for x, that is the same thing as solving for the molar solubility. So that would also be considered the molar solubility of silver sulfide. Okay, so you'll have to go that direction where you're given KSP and you have to figure out molar solubility. You may also be given the solubility. Sometimes they don't even call it molar solubility. Sometimes they just call it solubility. And you have to solve for K, KSP. Okay, I've got bismuth sulfide. And when it ionizes, which is going to happen very small percentage of the time, I get 2 bismuth ions and 3 sulfide ions. And if I set up an ice table for that, remember this solubility here, whenever it says the solubility of the actual compound itself, it's what X is equal to in your ice table. So if I set up an ice table for this and I have 0 plus 3X and I have 3X down here and plus 2X right there, all I have to do is take whatever the solubility is that they give me and plug that number in for each one of these X values, and then I can solve for KSP. So molar solubility or solubility of a compound is just equal to X in the ice table. So I'm looking to solve for KSP. Now writing out that expression, I've got bismuth, that's going to be squared. And then sulfide ions are going to be cubed. If I take this number 1 times 10 to the negative 15 and I plug it in here for my bismuth ion concentration, 2 times 1 times 10 to the negative 15 is just 2 times 10 to the negative 15. That gets squared. And then if I take X and I plug it in over here, then I get 3 times 10 to the negative 18 or negative 15. That gets cubed. And then for that answer, you get the actual KSP value, which is 1.1 times 10 to the negative 73. Do K values have units? No. They're ratios of how much product you get compared to how much reactant you start with. So very, very tiny amounts, but there is a tiny amount of it that will ionize. Okay, a lot of it is similar to ice tables. We're just dealing with solubility instead of acids and pH and all that stuff. Questions so far? Yep.
Do we have to, when we're doing the equation, do we have to write the as solid? Or can we leave it out?
You can leave it out, actually. They don't give points for that. As long as you know.
Okay.
As long as you know that this is solid right here and these are aqueous over here, you don't have to write it out every time. They don't give you points. They don't take off points if it's not there. You should write out the dissociation equation, but you can leave off those. All right. Yep.
Why do we need such small numbers? Why do we even know? Like they're so small.
Oh, because, well, this is just, I'm just giving you the basics, because then on the next couple problems we start to figure out if you mix a bunch of solutions together, which one is going to become a solid first or precipitate first, so we can figure that out based on their KSP values. So, I know, maybe who cares, but it happens. Okay, you need to know about the common ion effect. Have we talked about the common ion effect before? You feel like you've heard that. Well, that's at least good, because we have talked about the common ion effect before. And where is the common ion effect like a big deal that we just talked about at the very beginning of chapter 15? The B word. Buffers. Okay? The common ion effect is super important with buffers because you have a starting concentration of one of the products. And when you have a starting concentration of one of the products, it doesn't allow the forward reaction to happen as much, and so the pH doesn't change. That's the whole buffer thing. The common ion effect is the same idea when we're dealing with the solubility of salts. It's just the idea that if you have an initial concentration over there of one of the products, that it doesn't allow the ionization to happen as much. So this example says to calculate the solubility of calcium fluoride, and it gives you the KSP value, 4 times 10 to the negative 11. But we're taking that solid calcium fluoride and I'm dumping it into a solution that already has a concentration of 0.025 molar sodium fluoride. Now, is sodium fluoride soluble? Do you remember?
Yeah.
Sodium. Yeah, sodium breaks apart. It ionizes. Anything pretty much attached to an alkali metal will dissolve completely. or ionize completely. So I've got sodium ions and fluoride ions just floating around in that solution all over the place. And so it's the calcium fluoride that is not completely soluble. That's going to have a very small percentage of ionization. And so if I look at that equation, what's wrong with that equation? I need what? Two fluoride ions. The only difference between this and the first example problem that we did is that instead of, we start with 0 of calcium ions, I don't start with 0 of fluoride ions anymore. I start with 0.025 molar concentration of the fluoride ions. This doesn't matter because this is the solid. Okay, now you can go through and set up the ICE table and you can solve for X. Now, it's up to you if you want to rewrite all of this down, but I'm going to write it because there's just one thing I need to point out here. This is just setting up the ICE table. When I set this up for my KSP expression, your KSP equals X times 0.025 plus 2X squared, because I have 2 fluoride ions here. And then you're trying to solve for X. They gave us the KSP as 4 times 10 to the negative 11. Now this is kind of a tricky problem, which if you have your solver figured out, you could just plug it in. But you can do the same shortcut that we did with weak acids, where if the K value is so small, then if you add, then that means your X value is really small. So if you add anything that has X in it, it doesn't change the value very much at all. So you can just make that part of the equation 0. So then you get your KSP equals X times 0.025 squared, which is a much easier equation to work with to solve for X than that one. So just know you can cancel stuff out there too if you're adding or subtracting X from anything. Okay, let's say that we have magnesium hydroxide which is a weak base, which means it's also one of those partially not very soluble compounds. If I have magnesium hydroxide and a tiny percentage of it ionizes into magnesium and hydroxide ions, this would be solid, aqueous, aqueous. You need to know, you don't need to be able to do any calculations here, but you need to know qualitatively what happens if you add something that increases the pH of that solution. So you've got a solution, it's got magnesium hydroxide as part of it, but let's say I add like sodium hydroxide to this solution. If I add sodium hydroxide, it's going to become more basic, which is going to make the pH go up. So you need to think about what's going to go on. Since this is an equilibrium equation, if I increase the pH, that means that I'm increasing the hydroxide ion concentration. Le Chatelier's principle says that if I increase the hydroxide ion concentration, which direction is it going to shift? To the right or to the left? Okay, so it's going to shift to the left. Which means if it shifts to the left, you're going to have less ionization, less products being formed over here, which is the same thing as saying lower solubility. If I make this solution more acidic and lower the pH, I'm going to do that by adding hydrogen ions. Like I have my solution of magnesium hydroxide, maybe I throw in some hydrochloric acid. So I have some extra hydrogen ions in there. Those hydrogen ions, what do you think they're going to do with this hydroxide ion over here? They're going to form water. So the hydrogen, adding hydrogen ions to this reaction, this is one of those situations where it's like if you add something and it reacts with something from the reaction, then it's going to affect the equilibrium. So adding hydrogen, it's going to react with and remove hydroxide ions. If I take away hydroxide ions, according to Le Chatelier's principle, which direction is this going to shift if I take out hydroxides? It's going to shift to the right. And if it shifts to the right, that means it's going to make more of those things. So it's going to have greater solubility. So you need to be able to go through that process of if you increase the pH, what happens to the solubility? Does it increase or decrease? And if you make it more basic, what happens to the solubility? So you have to be able to go through and just use Le Chatelier's principle to figure out what happens in the reaction. Questions on that? I have 2 more examples. That's it. You thought that was all. You were wrong. Huh?
Could I see that last piece?
Yeah. Just write it down real quick. Okay. Okay, so here's a very common question. A very common AP question is, here are 2 solutions. I am going to mix them together. Is there going to be a precipitate that forms based on the concentrations of what you're given? So Q is coming back. Do you remember Q? Q is like when we had...
Reaction quotient.
Yes, this is a reaction quotient.
Isn't it also
And it, well, yeah, it's also key, but that's just different. We figured out Q the same way that you calculate K. You just plug in actual values instead of the values at equilibrium, and then you can compare and figure out what's going on. So I will let you write that down. And then we'll use Q to figure out the answer to this question.
When it says K like EQ, is that just regular K? When it says K like equation, or like K... it's
Equilibrium, just K?
Yeah, K EQ.
There is no KEQ.
Oh no, I saw
It's just K. It might be just K, the equilibrium constant. That just might be, usually those are KC, like based on the concentrations, or based on the pressures, KP. That might be a general term for both of those. Okay, so I have these 2 solutions with very tiny concentrations, and I'm going to mix them together, and I need to figure out if a precipitate will form. So in one container, I've got 0.0025 molar sodium phosphate. In one container, I've got 0.0025 barium chloride. And I'm going to mix them together in one solution. So what you need to think about, first of all, is kind of the overall double replacement reaction that might take place and what precipitate I would get out of this. Because individually, sodium phosphate, because of the sodium, is soluble. Barium chloride is soluble as well. So if this is my reaction, sodium phosphate, Na3PO4, plus barium chloride, I'm mixing those two things together into one solution. When those two things react, it's a double replacement reaction, I end up with NaCl and barium phosphate. Now, out of these two products, which one is going to be the one that would be the solid, if there would be one? NaCl is always soluble, so even though I'm going to maybe make that as a product, it's still going to remain ionized. And so it's the barium phosphate. Remember, this goes all the way back to like September when you had to do the double replacement, figure out which one is the solid product. So now I need to figure out, okay, barium phosphate would be the precipitate, the solid in this, but I just need to figure out if I have enough. Like I have these really small concentrations of these ions here, so I have to figure out if I have enough for them to actually combine together and form a solid. So the question is really, will the concentration be enough to precipitate? So what I first need to do, and I'm just going to give you kind of the steps. I need to do M1V1 equals M2V2 to find the concentration of barium ions and the concentration of phosphate ions. Because once I mix them together into one big new solution, the concentrations are going to be different because I'm mixing 50 milliliters and 50 milliliters. So total my V2 is 100. So I have to figure out what the new molar concentration of each one of those ions would be. And then when you do that, you get for barium 1.25 times 10 to the negative 3. And for phosphate, you get 1.25 times 10 to the negative 4. Now those numbers are the actual numbers. They are not at equilibrium. So that means that when you plug them into the equilibrium expression, what you're solving for is actually Q and not K. So I'm going to take a look at my barium phosphate again. And if I'm going to set that equal to and compare it to the K value of this, the KSP, is 6 times 10 to the negative 39. So I'm going to calculate Q the same way I would calculate K and compare. Now with barium phosphate, it's when it ionizes, I get 3 bariums and I get 2 phosphates. And so if I'm calculating QSP, I'm going to end up with my barium concentration cubed, my phosphate concentration squared. Okay, so I'm going to take those numbers, 1.25 times 10 to the negative 3, which was barium, cube that. Concentration of phosphate, 1.25 times 10 to the negative 4, square that. That gives me Q. Q is 3.05 times 10 to the negative 18. Q, remember, it's the same thing. And when we took the quiz on chapter 13 or whatever it was, and people were like, what is Q again? You just calculate Q the same way that you calculate K. It's just with values that aren't at equilibrium. And so when I calculate the Q value is 3.05 times 10 to the negative 18, all I have to do is compare that to the KSP value. And if it's bigger, then that means I'm going to have enough of this stuff to actually precipitate. If this value is lower, then I'm not going to have enough stuff, and it's not going to precipitate. So this value right here is greater than the KSP value for barium phosphate. And so that means that you have enough, and so yes, it will precipitate. you will get a solid that forms. Okay, so these problems are really, they're just applying a lot of the stuff that we've already done. We've done a lot of this procedural stuff already. It's just applying it differently to these insoluble things. Questions on this one? I got one more. Are you ready?
When you get like to the third, to the second power.
From right here.
Okay.
That goes here.
You make that equal to 6 times 10 to the
No, I calculate that number and it gives me this. Because these numbers aren't at equilibrium. This would be what I get. This would be the number I would get if I plugged in concentrations at equilibrium, but I don't have those numbers.
Okay, so it doesn't even matter.
It's just to compare. All right, here we go. Last one. When you get this question that says, which will precipitate first? This is one of those questions, and you have 3 things that are together in one beaker. It's helpful, just like in some of our other problems, to actually draw the beaker and see what's going on so you can figure out what the possible solids could be and then figure out which one will precipitate first. So I'm going to add sodium chloride. And when we're dealing with these KSP problems, you ionize everything. Well, by itself, lead nitrate is soluble, silver nitrate is soluble, okay? So lead, 2+ nitrates, because nitrates are always soluble, right? Silver and nitrate. Now, in the beaker, I'm going to cross out some stuff, but the reason why I'm crossing out stuff is different than the reason that I crossed out stuff before. Like in the acid problems, we crossed out stuff that don't affect the pH. In KSP problems, we're crossing off stuff from the beaker that are always soluble. Like nitrates are always soluble. Always. Every time. It doesn't matter what they're attached to. They are always going to ionize. Same with sodium. Oops. Soluble. Okay, so you're crossing out things in the beaker that are always soluble because they're never going to form a precipitate with anything. And so in this beaker, my only possible precipitates, it could be lead chloride, so I could get PbCl2, or I could get silver chloride, AgCl. And so the question is, which one is going to precipitate first and which one do I end up with? Because I have ions in there to give me 2 different precipitates, so which one is actually going to happen? So it's kind of like 2 problems. So for me, it's helpful just to set it up and kind of do the same process with each one separately, and then kind of figure it out at the end.
Is there like a list, like the soluble list?
Tyler, this is,
Did we do that in the beginning of the exercise?
yes,
There's like a list.
it's in like chapter 3 or something.
Chapter 3, okay.
Okay, so lead chloride, silver chloride. If I look at, I want to write out the ionization of each one of those separately. Okay, so lead and chloride ions. And why? Because I'm going to use the KSP values. For silver chloride, would break apart into silver and chloride ions. Okay, now I was given the initial concentration of lead nitrate, and I was given the initial concentration of silver nitrate, which just basically also gives me the initial concentrations of silver ions and lead ions. So lead, I have 0.00015, and it's only because it's a 1-to-1 ratio. For every 1 lead nitrate, I have 1 lead, and for every 1 silver nitrate, I have 1 silver. So that's why these concentrations are the same. Silver, I have 0.00035 as my concentrations. So if I write out the KSP expression, it's the concentration of lead. I didn't balance this. There should be 2 chlorides there. So that makes the chloride concentration need to be squared. The KSP expression over here is silver ion concentration, chloride ion concentration. Nothing gets squared there. All right, so I can look up the KSP values on the page number that I gave you. If I look up the KSP value for lead chloride, it's 1.6 times 10 to the negative 5. That's equal to, my lead concentration is 0.00015. I don't know the chloride ion concentration. That's what I want to solve for. So I'm going to put x squared. Because, go ahead.
Well, why doesn't the KSP value, like if it's greater or less, doesn't that just tell you if it's...
It could, but because you have like 1 squared and 1 not, it might not always work out that way. So you might just say, yeah, if you look at the K values and compare them, it might usually match up, but because of the way it ionizes, it's different.
X to the PV, like, you know, like plus X thing, you know that?
Well, this is, I already know the concentration of that in the
Just cross out
solution.
the X? Use such a low value?
Yeah, because it would be so small.
Okay.
Okay, so if I figure out the concentration of chloride ions here and the concentration of chloride ions here, what I'm solving for is how much chloride ions I need for the precipitate to actually form. So when I solve for X here, it equals the chloride ion concentration, which equals 0.327. And if I go through on this side, and I get 1.6 times 10 to the negative 10 equals, this was the KSP value for silver chloride that I looked up. My silver concentration, 0.00035 times X. X is the chloride ion concentration, 4.57 times 10 to the negative 7. These numbers right here tell me the concentration of chloride ions needed to precipitate. And so whichever one requires the least amount is going to be the one that precipitates first. And so since silver chloride requires the least amount of chloride ions, then silver chloride will precipitate first because it requires less of the chloride ions. And a lot of times it's going to match up with whichever one has the smallest K value, but not always because of things being squared and all of that. So you do need to go through that process and solve for the concentrations.
So why do they break apart in the first